Hello, this is Lab 5, the Faraday's Law Lab. I'm Edgar Gebhardt. Let's get started. So, the purpose of this lab was to use the model of a bar magnet falling through a metal tube to create a better understanding of Faraday's Law and to develop a computational Faraday's Law, a model of Faraday's Law from this experimental data. So, the basic models we used in this experiment, first we used the PHYS law, which is as seen, shows you the direction of magnetic field and can be used for magnetic force as well. We also have Faraday's law, which in the bottom you can see in its integral form, and then we also use Newton's second and third laws, the second being that force equals mass times acceleration, and the third being that every action has an equal and opposite reaction. So the preview of the results, the time for the magnet to fall experimentally was computed on average to be about 1.26 seconds, while the computational calculation of that time was about 1.348 seconds. So in the experiment, the magnetic north in the bar magnet was established using the magnetometer and the Firefox app on my phone. The bar magnet was then dropped through a tube of aluminum foil in order to get time readings, and the dropping was repeated 5 times in order to get a better estimate for the average time. And here's just one of those times. So as you can see, it fell kind of slowly. So the measurements for this experiment, the length of the aluminum foil tube was 0.3 meters, the width was 0.006 meters, the inner radius was 0.02 meters, the overall radius was 0.032 meters, the mass of the magnet was 0.024 kilograms, and from our calculations from my 5 experiments, I found the average time of falling was 1.26 seconds. And the magnetic dipole moment of the bar magnet was calculated back in Lab 3, and for me that was 5.384 joules per Tesla. So why can't we use a ferrous tube in this experiment? A ferrous tube has iron, and this could become an induced magnet, which would affect the falling magnet. And what happens to the magnet? So the magnet, as we saw, falls more slowly through the tube than it would in free space, allowing for the catching of the magnet if you're holding the tube. So for the coding, so first I use pre-lab 43 for a lot of the stuff in here, so first we establish the initial conditions, the length, width, inner radius, and overall radius of the tube, and then I enter the mass and the calculated mu from lab 3. Then for step 2, I reused my code from lab 3 for the magnetic field function, and then for the magnetic flux function, I used pre-lab 43, and it goes through and it calculates the flux from that initial magnetic field. And then I set up a gravitational force vector, which just says that the force is negative m times g in the y direction, because that's how we're holding the tube. Then I calculated the magnetic force on the tube on the magnet, created colors for the ring, created a vector for the current on the ring, and then for steps 5 and 6, as you can see, I calculated the magnetic field at the ring, calculated the direction of that and the angle, and then use that to find the overall magnetic force on the ring, which I then added up with the magnetic force on the magnet to find the total magnetic force in the y direction. And then I added that with the gravitational force to get the overall net force. And from there, we used Newton's second law to do the velocity update and position update formulas, and that created my program. So the computational readout created a model that sort of looked like this, where the blue was on top and the red was on bottom, and then ultimately the bar magnet went down until the blue was the only thing that was showing, and the program was finished. And this is the velocity versus time graph. As you can see, it's kind of goes down. The velocity is increasing in the negative y direction, then it slows down for a little bit, stays about constant, and then continues to increase until it falls out of the tube. And so the time in tube in seconds is 1.348 seconds. That's where we get that value from. So by Lenz's law, red is counterclockwise and blue is clockwise in this question because this is what slows the magnet down. A flip magnet would just have the current flowing in the opposite direction, but it should have about the same result in terms of speed. The computational model is fairly close to the experimental model here, but it could be improved by splitting the tube up into more rings or factoring in air resistance. And for the shape of velocity versus time graph, as we saw, the forces are in balance when the velocity is increasing and decreasing, but it's balanced for about a second in the middle of the descent. So that means it's going at a constant speed. So what if the resistivity of the conductor were reduced as close as possible to 0? So this means the braking force would increase to a point where the force on the magnet can counter the gravitational force, and it would prevent the magnet from falling through the tube at all. So it would be like levitation. And holes or slots were cut into the tube, so the number of rings in the model would decrease, leading to a reduced induced current and a reduced magnetic force, which would decrease the time that it takes for the bar magnet to fall through the tube. So the experimental time for falling was 1.26 seconds, while the computational time was 1.348 seconds. So this difference is due to some error either in my recording during the experiment or more likely in my calculations of mu, or the magnetic dipole moment, in Lab 3. However, the computational model was close to the experimental model, meaning that did model Faraday's law somewhat accurately. Thank you for watching.